Okay, so yeah, the call's now being recorded. If you have any questions, please type in the chat or put your hand up, and yeah, we'll ask you to read out your question. We've got Zhong with us today talking about GEC, a unified framework for interactive decision making in MDPs, POMDPs, and beyond. Han is a second-year PhD student at Peking University, and before that did his undergraduate studies in mathematics. And we've also got Tor hosting today. Tor, say hi to everyone. I think it's your first time.
Hello, everyone. Thanks, David.
And great, with that, Han, please go ahead, get started.
Oh, okay. So thanks for your kind introduction. Also, I would like to thank the organizers for inviting me here to present our work, GEC, a unified framework for interactive decision-making in MDP, POMDP, and beyond. I'm Han Zhong from Peking University. This is a joint work with Wei Xiong, Sirui Zheng, Li Wei Wang, Zhong Wang, Zhuan Yang, and Tong Zhang. Okay, as the title suggested, our work provides a new and unified framework for the general interactive decision making. Before giving the concrete definition of generalized eluded coefficient, I want to give an overview of the background and our main results. So reinforcement learning is a powerful tool for solving interactive decision making, where the agent interacts with the unknown environment and aims to maximize its own reward. Combining the reinforcement learning and deep learning, known as the deep reinforcement learning, has led to tremendous breakthroughs in many areas, such as the game of Go, autonomous driving, and poker. So from the theoretical side, core question is, can we perform sample efficient learning for the general interactive decision making? In general, there are several challenges to achieve sample efficiency in the interactive decision making. The first one is the exploration-exploitation trade-off, which is the intrinsic challenge for the online learning. And previous work shows that the naive exploration will increase in exponential sample complexity. So we need to design algorithms with strategic exploration. And the second challenge is the large state space. Modern I/O problems may involve millions to billions of states, but the classical tabular I/O suggests that for any online I/O algorithm, its regret bound is at least square root SA H square T. Here, S is the number of states, A is the number of actions, H is the horizon, T is the number of episodes. So when S is very large and the regret bound become vacuous, to avoid the dependence on S, we need to perform sample efficient learning for I/O with general function approximation. And the third challenge is the partial observation. We usually formulate the partially observable I/O problems as a partially observable macro decision process, POMDP. By learning the general POMDP, the regret bound should be A to the H, which is unacceptable for us. But this hardness result doesn't rule out the existence of large tractable subclass of partially observable I/O problems. So we need to identify tractable partially observable I/O models and design efficient algorithms for them. Previous works made great efforts to solve these challenges. For fully observable I/O, there are four notable general function approximation framework: the Bellman rank, Wissens rank, bilinear class, and Bellman eluded dimension. And these four general function approximation frameworks capture most of basic I/O problems, such as the tabular MDP, linear MDP, linear mixture MDP, and so on. For the fully partially observable I/O, there are also some identified tractable models, such as weakly revealing POMDP, latent MDP with sufficient test, decodable POMDP, low rank POMDP, regular PSR, and bilinear class. And these works provide different complexity measures and algorithms but they are seems separate. More importantly, for the fully observable IL and partially observable IL seems separate. So the question is, can we unify these different capacity measures and algorithms? So in our work, we first propose a new capacity measure, generalized eluder coefficient, GEC, that can capture nearly all known charitable IL problems. As this figure suggested, all these problems permit a row generalized eluder coefficient. In terms of algorithms, we propose 3 algorithms: a generic posterior sampling algorithm, a generic UCB-based algorithm, and a maximized tree explorer algorithm. And I want to emphasize that the proposed algorithms can be implemented in both model-free and model-based fashion under both fully observable and partially observable settings. For theory, we show that all the above 3 algorithms enjoy the regret of O tilde probably DGCH times square root t. Here, the DGC is the GEC of the IL problems, and H is the horizon, T is the number of episodes, or the O tilde probably DGCH times T2/2/3. And this sublinear regress shows that these 3 algorithms can learn low GEC problems sample efficiently. And our regret bound is sharp in the sense that they match existing regret bounds for Bellman-Ruder dimension and bilinear class. So in summary, we provide a new and unified understanding of both fully observable and partially observable IO. Then this is our main results, and then I want to formally define the interactive decision making. We consider the episodic interactive decision making, which is denoted by a tuple OA, H, P, and R. Here O is the observation space, A is the action space, H is the length of each episode, P is the collection of H functions, while PH of OH plus 1 condition on tau H denotes the probability of generating the observation OH plus 1, given the history tau H, which is the observation action sequences before the step H plus 1. And I is a collection of reward functions. We assume that the initial observation is sampled from a fixed distribution, and we also assume that the total reward in each episode is bounded by 1. In the general interactive decision making, we need to consider the general policy, which is a mapping of observation sequence. Yeah, pi is a mapping from the history and the current observation to the real-time decision. Given a policy pi, we can define its visitation probability p pi of tau h, which can be factorized by the product of p tau h and pi tau h. Here, the p tau h characterizes the randomness incurred by the transition dynamics, and the pi of tau h characterizes the randomness incurred by the policy pi. Also,
just a quick,
we can
just a clarification on the previous slide. What is the agent observing? Are they observing the rewards and the observation, or just the observation, or what is observed and what is known here?
Observe the observation and the rewards.
I see. Okay. Gotcha. And you just don't know the P's and you don't know the rewards, I guess. The functions.
Yeah.
Great. Thank you.
Oh, thank you for the question. So we can define the value for V pi is reward policy pi. So optimal policy pi star is a policy that maximizes the value function V pi, and the optimal value V star is the value function of the optimal function optimal policy pi star. For the online learning, we use the notion of regret to evaluate the the algorithm. Suppose an online algorithm predicts a sequence of policies pi 1 to pi t. Then its regret is defined as the cumulative difference between the optimal value v star and the value function of pi t. Our general function, our interactive decision making captures the MDP as a special case. The episodic Markov decision process is defined by SAH, P, and R. Since in MDP there is no partial observation, so the observation space is identical to the state space. Also, the transition dynamics satisfies the Markov property, which means that the next state only depends on the current state and action. In MDP, we only need to consider the Markov policy, which is a mapping from a state to a current action. Also, we can define the V function and the Q function. Here, the value function is the expected total reward conditioned on the current state, and the Q function is the expected total reward conditioned on the current state and action. For the optimal policy pi star, we also define the optimal Q function, Q star. It's known to us that the Q star satisfies the Bellman optimality equation, which means the QH star equals the Bellman operator TH operating on the QH plus 1 star. Here is the definition of the Bellman operator. Then we can define the Bellman residue. For any Q function, the Bellman residue is defined as the QH minus the TH QH plus 1. And if Q, for the Q star, the Bellman residue equals to 0. More generally, our interactive decision making includes POMDP as a special case. For the POMDP, the agent can only observe the observation, and so there is a latent state space and observation space. The transition dynamics also satisfies the Markov property. The next state only depends on the current state and action, and the observation is sampled from the emission matrix capital OH. Here, the capital OH of O conditional X is the probability of observing O as the state X and step H. We have mentioned that learning POMDPs in the worst case will suffer exponential lower bounds, but there result. For example, the weakly revealing POMDPs, suppose the observation space is larger than the state space and the minimal singular value of the emission matrix is lower bounded by alpha, then we can achieve a polynomial results. Also, for the decodable POMDPs, also known as the block MDPs, there exists an unknown encoder function phi h star, which is a mapping from the observation space to the latent state space, which encodes each observation to a latent state. There are also some other tractable, partially observable IO models, latent space with sufficient test, low-rank POMDPs. Also, our framework captures the PSR model, but I think I will not give the concrete definitions of PSR, and you can check our paper, or maybe we can discuss the PSR later. We also consider the functional approximation. We are given a general function hypothesis H. Here, the hypothesis can be either model-based or value-based. For the model-based hypothesis, each hypothesis denotes the transition dynamics and the reward function. The pi HF is the optimal policy corresponding to the model F, and the VHF, QHF is the optimal value function or the Q function corresponding to the model F. And F star is a true model. From the context on this dependence on the model F star. For the value-based hypothesis for MDP, and F denotes the Q function, and the pi HF is a greedy policy for the QHF, and the VHF is also the maximum of the Q function QHF. So in the value-based hypothesis, the F star denotes the optimal Q function. Throughout this talk, we require the realizability assumption, which means the H contains the F star. In other words, for the model-based hypothesis, H contains the true model, and for the value-based hypothesis, H contains the optimal Q function. Okay, this is our problem formulation, and now we are ready to give the definition of our capacity measure GEC. Before giving the formal definition of the GEC, I want to focus on the simplified MDP case and give more intuitions. So let's start with the value decomposition lemma. So by the value decomposition lemma, we can decompose the regret as these two terms. The first term is the Bellman residue term, and the second term we call this bias term. So if we additionally have the optimism condition, which means the V star is bounded by the VFT, then we know the regret is controlled by the Bellman residue term. So I want to remark that this optimism condition can be achieved by some UCB-based algorithm. For example, you can construct a confidence set, and then that contains the true model with high probability, and then you pick the hypothesis, the most optimistic hypothesis from this confidence set, and this UCB-based algorithm can guarantee the optimism. So now imagine that we have the optimism, and we want to minimize this Bellman residue term. And our observation is that to minimize this term, which is also non-trivial, there is a mismatch between the goal and the guarantee. So our goal is that the FT performs well on the unseen data tau t. Here the expectation is taken with respect to pi FT. Now let's consider what's the theoretical guarantee we can expect. It's worth to note that the FT, the selection of FT is based on the historical data. So we can only expect that the FT is good on the historical data. So in other words, this quantity is small. Here the expectation is taken with respect to pi fs, where fs is s is from 1 to t minus 1. So our guarantee is that the FT is good on the historical data, and we want FT to perform well on the unseen data. So to connect the goal and the guarantee, we somewhat require some property of the generalization from the past to the future. And this thing is simple in the supervised learning. If we have a TIID data sample from the fixed distribution, then with the realizability and the low hypothesis complexity, then we have a good generalization. But things are different in RL, since the trajectories are sampled from the different distributions, so the distribution exists all the time. So we require an additional structural addition to permit the generalization from the past to the future in an online manner. Motivated by this, we can define our simplified GEC as this. The smallest
just a quick question.
DGC such as this. Sure.
Could I see the previous slide for a sec, please?
Yeah.
Oh, just one slide back, if you could. Is there a slide before this with the two things that you're trying to compare? Like slide 17, I guess.
No, this is slides for our motivation of GEC.
Oh, on my screen I can see only the next slide. That's a bit strange. In any case, I'm looking at these squares in the Bellman residuals. Yeah, this slide exactly. So in the very bottom one,
yes,
we have the squares in the Bellman residuals. I'm guessing the FTs are going to be chosen in some set where those Bellman residuals are small, right?
Yeah, ideally we can consider the FT is chosen by some constraint, by some constraint from a confidence set. The confidence set, the constraint is some the Bellman residue square satisfies some property.
I see. Okay, right. Great.
Yeah.
Thank you.
Yeah, thank you for the question. Now we are going to define the simplified GEC. And so basically, the left-hand side of GEC is our goal, and we have mentioned before, and we call it the prediction error, since we need FT perform well on the unseen data. And the right-hand side is our guarantee, the training error. The FT is good on the historical data. So basically, the GEC directly connects the goal prediction error and our guarantee, the training error. So on average, if FT is consistent with the historical data, which means the training error is small, then the prediction error on the unseen test trajectory would also be small, is amplified by GEC. So more formally, we can show that if we have the optimism, low GEC, and small training error, then basically we have a low regret learning. So we have shown that the regret, if we have the optimism and the value decomposition lemma, the regret is bounded by the Bell distribution. And by the definition of GEC, the prediction error of DGEC cumulative training error. If we additionally have the training error is bounded by beta, then we have a regret of the square root of DGEC HT beta. And we want and I want to emphasize that for many UCB-based algorithms, the beta is only, for example, the linear UCB, UCL2, UCL VTR golf, and beta only has a logarithmic dependence in T. So now we have a perfect square root T regrets. So, but now the definition of GEC only can capture a restricted type class of MDP. And then I want to extend the GEC to capture the other MDP problems and even the partially observable IL problems. So the formal definition of GEC here, we are giving a hypothesis class H, a discrepancy function L, and exploration policy class PyExplore. The generalized eluder coefficient GEC HL PyExplore. Epsilon is actually positive real number. So the GEC is the smallest d such that for any sequences of the hypothesis FT and the corresponding exploration policies PyExplore FTH, this inequality holds. So compared with this simplified GEC, we have an additional Brane cost. So I want to say this we can just ignore this Brane cost since we can usually choose epsilon as a small quantity. For example, epsilon as 1 over HT, then this will not be the leading term in our final result. And compared with the simplified GEC, here the discrepancy function. And in this case, the exploration policy is simply the PyFS, and the discrepancy function is the Bellman rescue square. And I will give more examples of the choices of the exploration policies and discrepancy functions in the following slides. And I want to emphasize the flexible choices of discrepancy functions and exploration policies are pretty important for us to capture more IO problems. So intuitively, the GEC captures the hardness of the exploitation trade-off by comparing the out-of-sample prediction error with the in-sample training error. So now I will give more examples of the choice of exploration policies and the discrepancy function. So this is a simplified GEC I have defined before. This is for the Q-type problems, Q-type MDP problems. We just choose the exploration policy as the PyFS, the greedy policy, and the discrepancy function as the Bellman rescue square. And for the type problems for MDP, and then we choose the exploration policy as a PyFS circle H uniform A, which means that we execute the PyFS for the first H-1 steps, and then take a uniform action as step H. And the discrepancy function is also the Bellman residue square.
Oh,
For the,
Great.
sure.
We have a question from Tuan. Tuan, do you want to ask your question?
Yes, so I would like to ask, can you hear me?
Yep.
Yeah, I can.
I would like to ask about the Bellman Euler coefficient that we define. Is it true that this is a constant or could it depend on the time t?
I can't hear you clearly. Can you speak loudly? Seems
Here is the definition of the DEC constant. Is it true that it could be a constant for the history data, or it could be also depend on T and H?
Yeah, so your audio is a little bit hard to hear, Tuan, but I can ask the question maybe. So the question is whether or not the get could maybe depend on T and H is maybe not a constant. I think you're going to say that H is a constant, right?
Yeah, H is a constant. Yeah. Yeah, we focus on the final horizon problem, and here the H is a constant. And I think here the T is also
I think the question was more about the generalized Euler dimension, if it could depend on T and H.
Oh yeah. It can depend on the T and H. Yeah. Maybe for example, the GC can be the H times log T or something. Yeah. So the GC can depend on the horizon H, the number of episodes T, and the epsilon, I think, and some previous complexity measures, maybe the state sections or the dimension. Yeah, I will give more examples of the GC and say the concrete GC for specific problems. Okay. For the model-based problems, here's a pie chart that is either pi-fs or pi-fs circle H uniform A. Depending on the problems, is either Q-type or V-type, and the function is different. Here, the discrepancy function is the Hengel distance between the transition kernel of Ft and the transition kernel of the true transition kernel. So with these flexible choices of exploration policies and discrepancy functions, we can show that our GC can capture previous complexity measures. For example, for the Bellman-Euler dimension, we can show that the GEC is bounded by O tilde H dq. Here the dq is a Q-type Bellman-Euler dimension, and the O tilde omits some log dependence of the T and the epsilon. And the GEC is also bounded by the O tilde AH dV, where the dV is a V-type Bellman-Euler dimension. For the bilinear class, we have the GEC is bounded by O tilde H D bilinear. Here the D bilinear is the bilinear rank, and this holds for the Q-type problems, and the GEC is bounded by AH D bilinear for the V-type problems in bilinear class. For the Witness rank, we have the similar results. For the Q-type Witness rank, the GEC is bounded by HDQ over K Witness rank square. Here, the kappa Witness is some parameter in the definition of the Witness rank, and the GEC is also bounded by the O tilde AH dV over kappa Witness rank square. So this holds for the V-type problems. And our GC can also capture some partially observable IO problems. For example, for the POMDPs, we can choose the exploration policy as this. We execute the pi-fs at the first H-1 steps and execute the uniform discrepancy function is defined as a discrepancy function between the distribution induced by the FT and the true model. So with this definition of GEC, we can show that all alpha revealing POMDPs its GEC is bounded by O tilde polynomial of SAH and 1 over alpha. For the decodable POMDPs, we can show the GEC is only polynomial in SA and H. So more generally, we can show that the GEC can include the alpha generalized regular PSR as a special case. Here is a new PSR class identified by us. So the high level is that we impose some regular conditions on the observable operator representation of PSR. Then we can verify that nearly all non-checkable POMDPs satisfy this regular condition. And we can also show that the GEC is bounded by the polynomial factors of the previous complexity measure of PSR, for example, the PSR rank and HA and 1 over alpha. And two independent works also identify similar PSR class with regular conditions. So now we can conclude that the GEC can capture nearly all known checkable IL problems, and all these problems have a low generalized eluded coefficient. And so now we have shown that the GEC can capture nearly all IL problems.
Just a question.
Sure.
Can you say something about how this relates to the DEC?
Oh, yeah, this is a good and important question. Actually, I have prepared several slides in the discussion and so short question is currently I don't know whether GEC can capture can include the DEC and the DEC, or the DEC can include the GEC, and I think maybe these two frameworks are parallel and each has its own advantages and disadvantages. And I have prepared several slides in the discussion. Maybe you can discuss with the relationship with DEC later.
Sounds good. Great. Thanks.
Oh, okay. Thank you for the question. So now, then the next step is that we need to design algorithms that can solve all problems with low GEC. So before giving the specific algorithm design, we let's consider what the regret minimization problem should be. So by the definition of regret, the regret can be decomposed by the prediction error and the bias term. This is by the definition. Then by the definition of the GEC, the prediction error is bounded by the square root of DGEC times the cumulative training error and the bias term. So an ideal algorithm should minimize these two terms simultaneously. So the first question is how to control the training error. The training error is not available to the executed algorithm. For example, the discrepancy function may involve the Bellman operator or the chill transition kernel, which is unknown to the learner. And the bias term is all. So we need to approximate the training error by some loss functions and design an effective estimation to achieve a low training error. And the bias term is also hard to control since the V star is unknown to us. And we have mentioned before the UCB-based algorithms directly have the V star minus the VFT is less than 0, so we can control this term. But for other algorithm designs, such as posterior sampling, this property is not hold anymore. So can we permit other algorithm design? So I will first introduce our posterior sampling algorithm. So the posterior sampling involves the following 4 steps. First, we will choose an optimistic prior, which is proposed by Professor Zhong. The feel-good posterior sampling, I think Professor Zhang has presented his work in this seminar. Specifically, we can choose the hypothesis, the prior that favors the hypothesis with higher values. The prior is chosen as the P0F times the exponential of gamma VF. Here, the P0F is is based on the average of the. So in most cases, you can also choose the P0 as a uniform distribution in the over the hypothesis class. And then we need to choose a loss function to approximate the unknown training error. Here, the loss function is depend on the previous hypotheses and previous data. And I will give more examples of the loss function in the following slides. Then we can choose the posterior as this. This is a feel good optimistic prior, and this is a loss function. Based on this posterior, we can sample a hypothesis FT. Then we can simply execute the exploration policy for n batch times to collect samples. Here, the n batch is also a tuning parameter, and I will specify this later.
Maybe
So-
this is a super. Sorry, can I just a super naive question here? We have the loss in the exponential. Should there be a minus there? It seems we're going to sample
yeah,
have a high loss.
Oh yes, it should be approximately the minus training error. So it's just a so in this in our following choice the minus term sign is in the loss function. So it's more probably
okay. Yeah, gotcha.
Okay. Yeah. So I will first specify the choices of the loss function for the model-free case in the MDP. So in the model-free case, the training error is the Bellman residue square. So typically we want to use the TD error to approximate the training error, but there is a famous double sampling issue. So to address this double sampling issue, there are two strategies. The first one is a minimax formulation, which is used by the Golf or the conditional posterior sampling, and the loss function is chosen as cumulative TDL and minus this log term. So this introduced log term cancels the requires the companies type assumption to deal with. If you don't want this relative strong companies assumption, we can use the trajectory average loss. You can just execute the exploration policy for n batch times to collect n batch ID data, and then use the sample mean of the TD error to approximate the training error. The idea is very simple. The sample mean admits smaller variance. And for the model-based cases, the choice of the loss function is relatively simple. So basically, you just want to maximize the likelihood. So the loss function is chosen as the log probability of observing the historical data. For MDP, we collect the data XHS, AHS, and AXH plus 1S. So the probability of observing this data is PHF of XHS plus 1S condition on the current XHS, AHS. So for the POMDPs and PSRs, the loss function is similar. We can use the exploration policy to collect a full trajectory, and the loss function is the log probability of observing the full trajectory. So this is our posterior sampling algorithm. And I want to also formally define the UCB-based algorithm. So based on the UCB based on the past T-1 iterations, we can maintain a confidence set HT such that it contains the true hypothesis with high probability. Then we can choose the most optimistic hypothesis from this confidence set. Based on this hypothesis, we execute the exploration policies to collect data. And this UCB-based algorithm extends the previous UCB-based algorithm to a more general class, the class of problems with low GEC. The advantage of the UCB-based algorithm is the theoretical analysis is relatively simple and well understood. But the UCB-based algorithm is hard to implement since you need to solve a constraint optimization problem, which is hard to solve in practice. So to this end, the past T-1 iterations, we can choose a proper loss function, and then we choose the FT by solving this maximization problem. So this function can be regarded as optimistic modification of the loss minimization problem. And then based on this FT, we execute the exploration policy to collect data. And this maximize true explore algorithm is easy to implement, and it only needs to optimize an unconstrained objective. So a quick summary of the algorithm design. We want to minimize these two terms, the training error and the bias term. So to control the training error, we need to choose the proper loss functions to approximate the training error, and we need to choose proper exploration policies to collect data. To control the bias term, there are three algorithm designs. The optimistic posterior sampling, the UCB-based algorithm, and maximize to explore. So for theory, we prove that all these three algorithms enjoy the regret bounds. For the value-based approach for MDPs, if you use the minimax formulation with the assumptions, reliability assumption and the completeness type assumption, then we have a regret as the order of O tilde square root of DGC HT and times log H. If we don't want the completeness assumption, we can use the trajectory average. With only the reliability assumption, we have the slightly worse T to the 2/3 regret. For the model, this result also holds for the pole bilinear class, but I don't specify the details in this talk. For the model-based approach for the MDP, POMDP, and PSR, with only the reliability assumption, we have the the regret of the order of square root DGC times HT times log H. So this theorem shows that the interactive decision making is learnable by these three algorithms, and they match the existing bounds for Bellman-Luder dimension and bilinear class. So basically, we can conclude that the optimistic modification and a small low GEC and then effective training error estimation is basically a sample efficient learning. So this is our main theoretical results.
And Han, can you say something about why you get the T to the 2/3 when you don't have completeness? I guess the completeness you're talking about is the Q being when you apply the Bellman operator stays in the class, right? So where's the 2/3 from?
This issue also appeared in previous work, such as the bilinear. So for if we only have the reliability, then we can obtain a peg result as the order of 1/epsilon square, then convert to the regret minimization, then it's the T to the 2/3. Yeah, I think how to obtain the square root T regret for the bilinear class is still an open problem.
I see.
Yeah.
Thanks.
Okay, thank you for your question. So this is all. I want to make a comparison with the decision estimation coefficient, which is proposed by Faust et al. So both GEC and DEC captures most of non-tractable IO problems. And both GEC and DEC use a reduction-based idea, which means they convert the regret minimization problem to a new target. But the difference is that GEC converts the regret minimization problem to a in-sample estimation problem, but the DEC converts the regret minimization problem to another online learning problem. And the policy selection strategies are different. We just use the corresponding exploration to collect data, but the DEC need to solve a minimax optimization problem to obtain the exploration policy. And the algorithm design, GEC seems flexible in algorithm design. The posterior sampling, the UCB-based algorithm, and the maximized to explore are efficient for GEC. But for the DEC, it seems restrictive, only have a E2D algorithm. And the regret bounds, GEC can make the best known results for the bilinear class and the Bellman-Eluder dimension. DEC only have a suboptimal regret for the bilinear class. In terms of the lower bound, DEC also characterizes the lower bound for the IO problem. And currently, I don't know whether the GEC also captures the lower bound of the IO problems. So in this sense, I think maybe the DEC can capture more IO problems. But now I don't know whether we can, in the current definition, whether DEC can capture the low GEC problems. So this is, so I would want to make a brief summary. So in this talk, we propose a new complexity measure, GEC, that can capture nearly all known shareable interactive decision-making problems. The main spirit is that reduce the out-of-sample prediction error to the in-sample training error. And we propose 3 efficient algorithms for the interactive decision-making problems with low GEC. The key idea of the algorithm design is the optimistic modification training error. So we provide a new and unified understanding for both fully observable and partially observable IO. And this concludes my talk. Thanks for your attention.
Thanks, Han.
And
All right, so we're going to record for another 10 or 15 minutes if people have questions. Afterwards, once the questions run dry, we'll switch off the recording. Please feel free to just ask away now.
Maybe I can get started. So on the previous slide about the DEC,
yeah,
is it not the case that actually we could have a better bound for bilinear classes for the DEC since they have lower bounds?
seems not. So in this, their recent model phrase, they can only obtain the T to the 3 or 4.
So the lower bound is not matching for model free bounds?
Yeah, the original DEC paper seems hard to capture some model free cases. So they have a new paper to discuss the DEC for the model free classes. For example, the bilinear class for the model free classes. And in their new paper, their rebound is the T to the 3 over 4.
I see. Thanks. And there's a question from Rada asking if you can provide more information for your maximize to explore algorithm.
Oh, okay. Okay. So basically you can just regard this as TDL. So if we ignore this VF, then this is minimize the TDL. So the only difference of the maximize to explore is we add this optimistic modification of the loss minimization problem. And make the objective favors the hypothesis with higher rewards.
And when you say this is unconstrained, I guess the F is still constrained into your hypothesis class, right? And you hope that that's nice enough that you can solve this problem.
Yeah, that's right. But I think that's right. But in practice, for example, in practice, if a hypothesis is a neural network, so it's hard to the main problem is hard to construct a confidence set and solve this problem. So actually, this our algorithm can be implemented. So if we if H is all possible hypotheses, then this can be regarded as an unconstrained problem.
I see.
Yeah.
Yeah. Yeah, so Mohammed is asking a question. He asked, the ordered L1 and L2 optimization algorithms are tractable. Could you tell us which algorithms or problems from RL are tractable? Yeah, maybe the question is really about when can you expect to be able to implement this algorithm? But Mohammed, feel free to jump in and ask the question yourself as well.
Yeah. So basically, in the context of general function approximation, it's hard to say the algorithm can be implemented such as linear, the LSVI UCB like this. We can show that the LSVI UCB can be implemented in the polynomial time. So I think for the general function approximation, it's hard to say this. But our key point of the maximize to explore algorithm is that we don't need to solve this constraint problem, and this may guide the practice. Actually, in our paper, in our following paper, we have some experimental results to implement this result. But from the theory, I think it's hard to say the algorithms for the general function approximation has a polynomial time.
In the experiments, which classes are you using?
Oh, some modular modular classes, yeah, environments.
And what does the LHT-1 function look like in those problems?
Oh, it's like we both the model free and the model based. The loss function is like this one or the.
And you have experiments with both model based and model free?
Yeah, we have.
Daniel?
Yeah, hi. Thank you for great presentation. I have a question regarding the posterior sampling algorithm. Do you just sample once from these posterior that you construct here? Because I know that even for tabular MDPs, it is like to ensure optimism of this sample that you like. It might be problematic, and people usually sample several times in order and then pick the truly optimistic sample there.
Yeah, in our algorithm, we only need to sample one FT. This is because of the optimistic prior added like this. So this optimistic prior will encourage the exploration. So for this, if we use this optimistic posterior sampling, we can just sample one hypothesis.
Okay, if there are no more public questions, I'll stop recording now.